welcome back to another explainer. Today, we're cracking open the ultimate builder's toolkit for Java programmers, user-defined methods. If you've ever stared at a massive scrolling wall of text in your code and thought, man, there has to be a cleaner way to do this, well, you're in the exact right place. Our goal today is to totally demystify Java methods so you can write cleaner, incredibly efficient, and dynamic code that actually makes sense when you read it.
Let's kick things off with a quote from our source material that perfectly sets the stage for today. Methods are just like black boxes where a user need not to be aware of the logic or code running behind the application. Think of your program like a massive factory assembly line. A method is just a self-contained black box right on that line. You feed raw materials into one end and a finished product pops out the other. You don't need to see the messy, noisy gears turning inside every single time you use it. You just need to know it gets the job done.
Here's our quick roadmap for today. We're going to cover why we need methods, the anatomy of a method, invoking Java methods, passing data, pure versus impure methods, and finally, the power of overloading.
Okay, let's jump right into section 1, why we actually need methods. Writing code line by line is fine for a quick, tiny script, but as your programs grow, that linear approach turns into a tangled spaghetti code nightmare. Methods save us by offering 4 absolutely massive benefits. First off, they reduce complexity by chopping a giant problem into small, bite-sized parts. Second, and this is probably the biggest one, is code reusability. You define a block of code once, and you can call it 1,000 times from anywhere in the program. Because you're reusing code instead of endlessly copy-pasting, you dramatically cut down the length of your program. And lastly, just like our black box analogy, it hides complexity. You just call a function, and the method does all the heavy lifting behind the scenes. Moving right along to section 2, the anatomy of a method. Now, before we can use a method, we have to define it. And the very first line of that definition contains 2 concepts that get mixed up all the time, the prototype and the signature. So the method prototype is that entire first line. It's the grand introduction to the compiler, telling it the return type, the method's name, and what data it takes in. The method's signature, however, is a much smaller, very specific piece of that prototype. It refers strictly to the list of parameters and their data types. Think of the prototype as the entire ID card, while the signature is just the unique fingerprint. So let's break down the actual syntax. We usually start with the access specifier, like public, which dictates exactly who is allowed to use this method. Next is the return type. If you see void, it means this specific method doesn't send any value back. It just performs an action and stops. Then we have the method name itself, followed by parentheses. If those are empty, it means the method requires 0 parameters to run. Below all of that, enclosed in curly braces, is the body of the method, the actual gears inside our blackbacks. On the flip side, you might have a method where the return type is an int, and its signature specifically requires 1 integer variable to function. All right, section 3, invoking Java methods. We've built the machine, but how do we turn it on? Well, Java calls this invoking a method. And there's a hard line drawn between the 2 ways you can do this, depending entirely on whether the method is static or non-static. Static methods belong to the class itself. Because they're class-level tools, you can invoke them directly just by using the method's name or the class name dot the method name. Super easy and immediate. Non-static methods, though, are instance methods. They don't exist in a vacuum. They require you to bring a specific object to life first using the new keyword. You literally have to create an instance of the class and then use that specific object to call the method. Which brings us to section 4, passing data, or parameters explained. Now, the crucial part is feeding raw materials into our methods. We're talking about arguments or parameters. But there is a vital distinction between actual and formal parameters that trips up a lot of learners. Actual parameters are the real, concrete pieces of data you are passing when you make the call, like the numbers 10 and 20, or a variable you've already defined. Formal parameters are the temporary placeholders sitting up in the method's definition, waiting to catch that real data. So think of it this way. The actual parameters throw the ball, and the formal parameters are the glove that catches it. So how does that data actually travel into our black box? Java uses 2 distinct mechanisms here, call by value and call by reference. When you use call by value, which happens with primitive data types like int or float, Java creates a safe duplicate copy of your data and hands it to the method. They exist in completely separate memory spaces. So whatever the method does to the copy, your original actual parameters remain completely untouched and safe. Call by reference is used for objects and arrays. Instead of passing a copy, Java passes a reference to the original memory address. They share the same memory. meaning any changes the method makes to the formal parameters will automatically and permanently alter your original actual parameters.
To put this into perspective, say your formal parameters receive the values 10 and 5 using call by value. When that first variable is modified inside the function, the original variable down in your main program remains completely isolated and unaffected. However, with call by reference, an object variable holds a reference address, like memory cell 10.4. Both the actual and formal parameters point to that exact same spot. So when the method multiplies a value by 2, it is directly altering the raw data living at that shared address. It's a fundamental difference you absolutely have to keep in mind.
Next up, Section 5, Pure versus Impure Methods.
We can classify methods based on whether they alter the state of an object. Pure methods? They are your safe, predictable accessors. If you give them the same input, they will always return the exact same output without leaving a footprint. They don't change any instance variables. They have absolutely no side effects. Think of something like math.square root. It just calculates and gives you a number. Impure methods, however, act as mutators. They actively go in and change the state of the object, modifying the values of instance variables. Because they have side effects, they require much more careful control in your architecture, so you don't accidentally overwrite crucial data.
And finally, let's look at Section 6, the power of overloading.
Imagine having a tool that automatically adapts its shape depending on the materials you hand it. That is essentially method overloading. It happens when you define 2 or more methods in the exact same program that share the exact same name, but have completely different method signatures. And remember, the signature is the parameter list. This is a form of static polymorphism. Because the parameters are different, the Java compiler uses something called early binding. It looks at the arguments you are passing during compile time and instantly knows exactly which version of the method to trigger.
Seeing this in action is pretty fascinating. Picture a program with 3 distinct methods, and they're all identically named calculate area. Normally, this would cause a massive error, right? But it works beautifully here because their parameter signatures are completely unique. The first takes a single float to find the area of a circle. The second takes 2 int variables for a rectangle. The third takes a single int for a square. You just call the method name, pass your specific data, and Java flawlessly routes it to the correct logic block. It makes your code so incredibly intuitive to read. By mastering all of this, from parameter passing to static polymorphism, you really transform your methods from just basic blocks of code into a highly organized, dynamic architecture. So as we wrap up this explainer, I want to leave you with a thought. How many awkwardly named methods in your current projects could be unified into one elegant overloaded tool? Take these concepts back to your IDE, start building your own black boxes, and watch your code become cleaner and more powerful than ever. Thanks for hanging out and learning with me today, and keep coding.